Let's talk about identities. Last year, when it came to trigonometry, we learned about the Pythagorean identity. And that was really the only one that we had touched on. We also looked at, the sine, cos, tan, secant, cosecant, cotangent, all of those relationships. But really the only identity we learned above those was the Pythagorean identity. Well, this year we're going to be looking at a whole bunch of different identities. And we're going to start with what we call the compound angle formulas or identities. Okay, so you might hear these referred to as identities or formulas, but basically they look like this. First one says that if you have sine of A plus B, so sine of two angles added together, that's the same as saying sine A times cos B plus cos A times sine B. Okay, that's the first one. The second compound angle is cos of A plus B is equal to cos A cos B minus sine A sine B. Okay, and then the third one is tan of A plus B, and that's equal to tan A plus tan B divided by 1 minus tan A times tan B. Now, if you notice, all three of these are situations where we're adding two angles together, A plus B. But we also have some compound angle identities for when we're subtracting. So we have sine A minus B, and that's equal to sine A cos B minus cos A sine B, like that. We have cos A minus B equals cos A cos B plus sine A sine B, and we have tan A minus B equals tan A minus tan B divided by 1 plus tan A tan B. So you have those previous three where we're adding together, and now you have these three where we're subtracting. Now, you don't have to memorize these 6 identities, at least not likely for this course. Maybe in university you'll have to memorize a lot of identities, but for now, usually you're allowed to have either a formula sheet or you'll be given the identities or something along those lines, right? But it is good to be familiar with these, so we're going to practice using them in lots of examples, okay? And when it comes to proving these and showing where they come from or deriving them, we're going to have another video where we talk about how we find every single identity that we talk about, okay? So I'm going to show where they come from, but that's for another video. For this video, we're going to just look at them and then do some examples, okay? So let's do an example. Let's say I have sine of 75 degrees, and let's say I want to figure out what this is, but I can't use the calculator. What should I do? Well, the trick here is to change it from sine 75 to sine of two angles combined together, two angles that we could find the sine and cos of on their own, right? So if you think about it, what adds to 75? Well, a lot of things, but what are some of the angles that we know about? Well, we know about 60 degrees, we know about 30 degrees, we know about 45 degrees, right? We know about all those. So what if I did sine of 45 plus 30? That adds to 75, right? And now what I could do is I could use that compound angle identity, or one of them, to split this thing up into something I can really solve, right? So if you remember sine of A plus B, if you look at that one, it's going to look like this. Sine of 45 degrees times cos of 30 degrees plus cos of 45 degrees times sine of 30 degrees, right? That's just cos of A plus B, right? You expand it like that. And this is going to equal, well, what's sine of 45? Well, if you look at your unit circle, or if you remember from your special triangle, you'll recall that sine of 45 is equal to root 2 over 2. If you're asked to find cos 30, again, look at the unit circle or the triangles, whatever you want to use, and you'll see it's root 3 over 2. Cos 45 is also root 2 over 2, and sine of 30 is a half. right? So whenever you're doing these types of questions, you want to have with you a list of those identities and your unit circle. That way you can just reference them quickly and you can figure these out, right? You don't have to memorize. Now we do have to simplify this. So I'll say we have root 2 times root 3, that's root 6 over 4, right? 2 times 2 is 4, plus root 2 times 1 is root 2, 2 times 2 is 4. So you're going to get root 6 plus root 2 over 4. And they might ask you to simplify this in some different ways, but this is, I think, probably good enough. Okay? Let's look at another example. Let's say you're given tan of 23 pi over 12, and you have to solve for this. What the heck would you do? Well, let's think about what 23 pi over 12 is equal to, right? Well, if you think of tan, it's always the sine values divided by the cos values. But what we have here is tan of 23 pi over 12. Well, all these fractions are either over 3, 4, or 6. There's nothing really over 12. So the idea would be to change that 23 pi over 12 to two numbers that we do have. We want to change 23 pi over 12 into two of those added together. So what could I change this to instead of 23 pi over 12? And this might take a little bit of work to figure out. But think of what adds to 23 and then just try, right? Well, what if you tried 20 pi over 12 plus 3 pi over 12? Well, you might say, well, those aren't on the circle. True, but we can reduce them, right? 20 over 12, that's going to reduce to what? Well, 5 pi over 3. 3 pi over 12 reduces to pi over 4. Are those on the circle? Yeah, they are. So those are both on the circle. We can use those. So now that we have that, I can say, all right, this is tan of 5 pi over 3 plus pi over 4, right? So you just want to break up that 23 over 12 into two fractions that are going to reduce. So I knew to do 20 and 3 because I knew 3 and 12 can reduce, and I knew 20 and 12 could reduce because 20 and 12 are both even numbers, right? 2 can go into both, and actually 4 came out of both. And 3 over 12, they're both divisible by 3, right? So that was just kind of jumping out to me like, oh, 20 and 3, because they're both divisible by something that 12 is also divisible by. So that's what you got to do. And that's not the only way to do it, right? There's other combinations that you could come up with. That was just one, right? So I would encourage you to try to do it with a different combination and see if you can get an answer. Now we have to use the compound angle formula here, or the identity, to split this thing up into things that are actually solvable, right? So if you think of tan of a plus b, we're going to use that identity. So it'll be tan of a, or 5 pi over 3, plus tan of b, or tan of pi over 4, divided by 1 minus tan a, which is 5 pi over 3, times tan b, which is pi over 4. So that's what you get. And now you might say this looks like a big mess, but what's nice is each of these individually we can figure out, right? And then we can plug them in. Tan of 5 pi over 3. Well, if you go to 5 pi over 3 on your circle, and you do the sine divided by cos, negative root 3 over 2 divided by a half, the 2's cancel, and you're just left with negative root 3. So negative root 3. You do that same thing for all of these, right? Go on your circle for tan of pi over 4 and divide the y and x values, right? And you're going to get 1. Okay, and then on the bottom you plug in the same numbers, just like that. And that's going to equal 1 minus root 3 divided by 1 plus root 3, right, if you simplify all this. And one thing you want to make sure of for your final answer is that you don't have a radical on the bottom, right? So what you're going to do is you're going to say 1 minus root 3 divided by 1 plus root 3. That's our answer so far, right? You're going to multiply that by the conjugate, which means you multiply by 1 minus root 3 over 1 minus root 3. So this is just the conjugate of this, right? Instead of 1 plus the thing, you have 1 minus the thing. And what that allows you to do is when you multiply that out, you're going to have some terms cancel. So 1 times 1 is 1. 1 times negative root 3 is negative root 3. Root 3 times 1 is plus root 3. And then root 3 times negative root 3 is negative 3. And as you can see, those middle two terms cancel. On the top, you can also multiply these out. 1 times 1 is 1. Then you'll have negative root 3 plus 3, right? So on the bottom, you're going to have just 2, 1 minus 3. Well, negative 2 actually, right? 1 minus 3 is negative 2. And on the top, you have 1 plus 3, which is 4, minus 2, root 3. And then you can cancel a 2 out of all of these, right? You can actually divide them, and you'll have negative 2 plus root 3. and that'll be your final answer. So you can always multiply by this conjugate fraction here in order to get rid of your radicals on the bottom and simplify your answer. Okay? And that's that. We'll do one more example using the compound angle identity. So let's say you have sine of x minus pi. So for this one, we're not going to make you split it up. So how would you simplify this? Well, it's sine of a minus b, so we're going to use that identity. So we'll get sine x times cos of pi minus cos of x times sine of pi. Well, if you recall, sine of pi is equal to 0, right? And so this is just going to go away. And then cos of pi is equal to -1. So you're just left with negative sine x. So this is the same as this. So if you ever have sine of an angle minus theta, if you ever have sine of an angle minus pi, that's the same as saying negative sine of that angle. Okay? All right. Let's move on now to another type of identity. This is called the double angle identity, or the double angle formula, whatever you want to call it. And just like the compound angle, there are several of these. You could say sine of 2 theta is equal to 2 sine theta cos theta. Or we could say cos of 2 theta is equal to cos squared theta minus sine squared theta. And for cos 2 theta, there's actually several. We could also say this is equal to 2 cos squared theta minus 1, or we could say it's equal to 1 minus 2 sine squared theta. So you have many options here for this one. It just depends on what's convenient for your situation, right? And again, we'll do a video about how to derive these and where they come from, but you may have a suspicion that these are related to the Pythagorean identity because of the cos squares and the sine squares, and you would be correct in saying that, but we'll check that out in the video. And then finally you have tan of 2 theta, and that's equal to 2 tan theta divided by 1 minus tan squared theta. Okay, so have these in your notes, and we're going to do some examples. Okay, so for the first example, I'm going to say that if cos of theta is equal to 3/5, and we're told that theta has to be in between 0 and pi over 2, so within that first 180 degrees is what that means, right? With all that in mind, we want to find sine 2 theta, cos 2 theta, and tan of 2 theta. So if this first part's true, find all of this. Okay, that's an interesting question, right? So what you can do first is you could say, all right, let's find cos of 2 theta. And the reason I want to find cos of 2 theta is because the equation for cos of 2 theta is equal to 2 cos squared theta minus 1, or at least that's one of them, right? From up here, it's this one here. So we can use that to find cos of 2 theta right away, right? So cos of 2 theta is equal to 2 times cos theta squared, so 3/5 squared minus 1. And we can just go ahead and figure this out, right? So that would be 2 times 9 over 25 minus, I want a common denominator, so I'm going to make that 1 into a 25 over 25. And so now you have 18 over 25 minus 25 over 25. That's going to equal -7 over 25. So that's what cos of 2 theta is equal to, right? We still don't know theta, but that's okay. But we know cos of 2 theta. All right, so what does this mean that we have? Well, if you want to illustrate what we have so far, we could say that because the cos of 2 theta was a negative answer, it means we're going to the left, right? Like that. So this is your angle 2 theta. And because -7 over 25 was the cos value, that means this value here is -7 over 25, right? It's this distance. Or alternatively, what you could say is that because cos is equal to adjacent over hypotenuse, really what you could say is that this length here is -7 and the hypotenuse is equal to 25. You also have that choice, right? You could do that. And that's actually what we're going to do here, because if you have two sides, you can find the third side, right? All you have to use is Pythagorean theorem. So if you use the Pythagorean theorem and say a squared plus b squared equals c squared, you do 7 squared plus b squared equals 25 squared and solve for b. B is equal to 25 squared minus 7 squared square rooted. Therefore, b is equal to, that comes out to 24. So this here has a length of 24. Well, now you can find sine, right? Because sine of 2 theta is just going to equal the opposite over the hypotenuse, which is 24 over 25. So now I've found both cos and sine of 2 theta. All I have to find now is tan of 2 theta. Well, tan of 2 theta is just those two answers divided by each other, right? Tan of 2 theta is equal to sine of 2 theta divided by cos of 2 theta. Or you could think of it as it's just equal to your y over x, right? And so in this case, your opposite over adjacent, another way to think about it. So 24 over negative 7. So we can write that in, and you'll get negative 24 over 7. That's tan of 2 theta. So we came up with tan of 2 theta, sine of 2 theta, and cos of 2 theta without knowing what theta is, right? And it wasn't necessary. All we had to know was that cos of theta was equal to 3/5. That's all we had to know. Okay? And again, let me just stress this point. The reason I knew it was in the top left quadrant was because the cos value was negative, so it was going to the left, but I knew it wasn't going to the left like this, right, going down. The reason I knew it was in the top left and not down there was because they said theta has to be between 0 and pi over 2. So the original theta is between here, right, in this section. So 2 theta can't be bigger than 180, right, because at most theta would be like right here, and if you double that, you'd be like right here, right? So theta, because it's in that first quadrant, it means that 2 theta must be somewhere in the second quadrant over here. That's how I knew that. Okay, let's do another example. Let's say we have 2 tan x minus tan 2x plus 2n equals 1 minus tan 2x tan squared x. Okay, and let's say the question here is to find n. So this little n right there. Let's find that. I think one thing we could do is we could write everything so that all the angles are just x. Because right now, you're taking the tan of angle x, but here you're taking the tan of angle 2x. Right, here's 2x, here's x. So let's change all these so that they all have the same angle, right? So we'll do 2 tan x minus, this is going to become 2 tan x divided by 1 minus tan squared x. So it looks like it got a little bit more complex than it is here, but the angles are both x instead of 2x. So now things are becoming compatible. That's what we want. Plus 2n is equal to 1 minus, same thing here, 2 tan x over 1 minus tan squared x times tan squared x. Now what I'm going to do, just to help me look at this without getting a headache, I'm going to say let tan x equal b. All right, and if you let tan x equal b, what you have is 2b minus 2b over 1 minus b squared plus 2n equals 1 minus 2b over 1 minus b squared times b squared. And actually, those two b's can go together, and you can make it b cubed on top, like that. So this is just to make it a little bit more manageable, right? Now to get rid of these denominators, let's just multiply everything by 1 minus b squared. So you get 2b, 1 minus b squared, minus 2b, plus 2n times 1 minus b squared equals 1 minus b squared minus 2b cubed. So now everything's on one line. We don't have any fractions, right? That keeps things simple. Now let's solve for that 2n. So you get 2n is equal to, on the right you have 1 minus b squared minus 2b cubed. I'm going to move over this negative 2b, so that'll be plus 2b. Move this thing over, and if you do that and you also expand it, you're going to get minus 2b plus 2b cubed. And then I'm going to divide this right side by the 1 minus b squared, just to get the 2n alone, okay? So you get to this step here. Now, we got to take a look and see if anything cancels out, right? Like I have a minus 2b cubed plus 2b cubed. Those cancel. The plus 2b minus 2b cancel. And all you're left with is 1 minus b squared over 1 minus b squared, which of course is just going to equal 1, right? So I get 2n is equal to 1, divide both sides by 2, n is going to be equal to 1/2. And so that's going to be your answer. Now let's do another example. Let's say I have cos of pi over 12, and I want to know what that's equal to. And one piece of information I'm given is that cos of pi over 6 is equal to root 3 over 2. And we knew that, right? From the unit circle, we have that information. But with that in mind, we could say, all right, well, cos of pi over 6 is equal to cos of 2 times pi over 12, right? Well, we know cos of 2 pi over 12, if we use the cos of 2 theta equation that we looked at, that's going to equal 2 cos squared pi over 12 minus 1, right? Because cos of 2 theta equals 2 cos squared theta minus 1, again, from those formulas, right? And we already know what this is equal to, right? Because it's equal to cos of pi over 6, which is root 3 over 2. So I can equate this to root 3 over 2. So now I have this expression here, and we can solve for cos of pi over 12, because that's what we want to know. I want to know what cos of pi over 12 is. So let's just isolate the cos pi over 12, right? Like I'll add 1 to both sides. So you'll have 2 cos squared pi over 12 equals root 3 over 2 plus 1. And then to get rid of this 2 on the front, I'm going to divide both sides by 2, just like that. And then you can square root both sides to get rid of that square, right? So cos of pi over 12 is going to equal the square root of root 3 over 2 plus 1 over 2, right? The square root of all of this. And when you take the square root of something, of course, you get plus or minus, right? So that's what my answer is. It's this mess here. All I have to do is clean it up a little bit, right? So I could say it's equal to plus or minus. We have plus or minus the square root of, well, 3 over 2 divided by 2 is root 3 over 4. And 1 over 2 is just a half, right? So you get something like that. And if you want to simplify it further, I guess you could say plus or minus. You can make this fraction here into 2 over 4 if you want. So there's a common denominator. So you could say root 3 plus 2 over 4 square rooted. And then you can just square root the bottom. So you get plus or minus square root 3 plus 2. And that would all be over 2. So you could write your final answer like that if you want, right? But it's up to you. Now, one important thing to remember is we said plus or minus here. But if you recall the beginning of the question, we were told that we're trying to find cos of pi over 12, right? Well, if you remember where pi over 12 is half of 30 degrees, right? It's half of pi over 6. So you're going to be like right here. That's in the first quadrant, right? So your cos value of that is going to be positive because you're going to the right. So really, we should only take the positive answer here, right? So we don't have to put plus or minus. We're just going to take the positive, right? And it's because we expect a positive cos value in that first quadrant, all right? So when it comes to these types of questions, you always have to be looking at that sign on the front and double checking that it makes sense by the end of your question, okay? Now, let's look at the cofunction identities. Cofunction identities. So we have sine of x equals cos pi over 2 minus x. Okay, that's 1. We also have cos of x equals sine pi over 2 minus x. We have tan of x is equal to cotangent pi over 2 minus x. And we have cotangent x equals tan pi over 2 minus x. You could also say that secant x is equal to cosecant pi over 2 minus x. And finally, you could say cosecant x equals secant pi over 2 minus x. So that's quite a bit, right? But again, you don't have to remember them. You just have to be familiar with them. So I guess if you had something like sine of pi over 2 and you want to change that to cos, it would become cos of pi over 2 minus pi over 2, which would be equal to cos of 0 which we know the answer to, right? Cos of 0 is equal to 1. So cos of 0 is 1. Sine pi over 2, that's also equal to 1. That's why these are equal to each other, right? So sine and cos have that special relationship, just like secant and cosecant would, right? Because they're just the inverse of cos and sine. And tan and cotangent also have a relationship because they're just the inverse of one another, right? So let's look at some situations here. Say I have an axis like this. So here's 0, here's pi over 2, right? And let's say I have this point here at the top. That point is 0, 1, right? That 1 is your sine of pi over 2. But if you look at a point here, and we'll say that's the point 1, 0, it's the exact opposite coordinates. That 1 on the front, same 1 that's there, that's cos of 0. So you can really see from that last example that this makes sense, right? You could also look at something where we're dealing with tan, right? You could say, okay, here's your plane. You have this angle here, pi over 3, and then this angle, which is half of that angle, which is pi over 6. And for these coordinates, you could say this one up here is 1/2 and then root 3 over 2, whereas the coordinates for this one here are root 3 over 2 and a half. So they have the opposite coordinates from one another, right? So if you took tan of pi over 3, so tan pi over 3, it's sine over cos. So you get root 3 over 1 because the 2's just cancel, or you could just write that as root 3. But if you did cotangent of pi over 6, so I'll take the cotangent of this other one, you do the opposite. It's cos over sine. So root 3 over 2 divided by a half, 2's cancel, you also get root 3. So you get the same answer for those as well. So tan of this is equal to cotangent of this, and vice versa, right? So that's that relationship. So you can see somewhat how these relationships are going to make sense, right? Sine and cos, because sine of one angle is equal to the cos of another angle if those two angles have that relationship, right? Okay, and then finally, just as a review of what we've talked about before, the Pythagorean identity. So this one you should remember. It's just sine squared theta plus cos squared theta equals 1, right? Because that's a squared plus b squared equals c squared in a triangle where your hypotenuse is 1 and this is your theta. That means your opposite side is sine theta and your adjacent side is cos theta. So a, b, and c. So it's just the Pythagorean theorem, but we're using these terms instead. And you could rearrange this and you can get some things like tan squared theta plus 1 equals secant squared theta, or maybe a cotangent squared theta plus 1 equals cosecant squared theta, right? You can rearrange this and use it in all kinds of ways. Those are just a few. So again, that should be review from last year, but keep that in mind because we're going to use that one as well.